Okay, hello everyone. This is the third or fourth lecture on natural language processing, which is an application of deep learning. And uh, we are going to be talking today about an extremely interesting and important topic called neural machine translation. Okay. All right. So why is this such an important topic? It's from its own point of view, machine translation is an extremely important topic. It enables communication between people who don't speak the same language. But it is also important from the point of view of commerce in terms of companies like Amazon and so on selling their products, and they want to communicate with customers all over the world and so on. And it's an intellectually challenging problem. Machine translation has been a topic of great interest. Even when I was starting out as a graduate student many decades ago, I was actually interested in this topic of machine translation. It seemed like a interesting and well-defined problem to take something in English and converting it into German or Hindi or Kannada or something like that. How would you do that by algorithm? So it's an important topic. And what has happened is a major revolution has occurred. The early methods were looking at language models, syntax, semantics, things like that. And they only took us so far. And there were many examples of how machine translation failed. For instance, they were trying to translate from English to Russian or Russian to English. In one language, the sentence said, "The spirit is willing, but the flesh is weak." So they wanted to translate it from, say, English to Russian. And in Russian, it came out as the vodka is strong, but the meat is rotten, right? It came out sounding like that. Literally, it was correct. The spirit was vodka and flesh was meat, but it was a totally nonsensical translation. So how would you get meaning into a translation so it means exactly what was said, or at least close to that? So that's the problem of machine translation. And the early methods were doing very poorly. And until this whole revolution of deep learning came around, made a dramatic improvement. And some of the claims are that the neural machine translation, which is machine translation based on neural networks or deep learning, is almost as good as humans. So they've done some metrics to see how good is this. And it's almost as good. Of course, it cannot be absolutely perfect in every setting because there are all kinds of subtleties in language. So that is something is a probably cannot be said it's 100%, maybe 95%, 99%, something like that. It's good. Anyway, so it's an interesting, intriguing problem. And we want to study this topic not just for the sake of knowing about how we do machine translation. You know, your interest may not be natural language, you might be something else. Maybe computer vision is your interest, or recommendation systems, or just the theory of deep learning is your interest. Still, it's a very worthwhile topic to look at because it brings in so many ideas that are useful in other applications. First of all, the idea of RNN, we already looked at, recurrent neural networks, where we are dealing with the time sequence. That itself is an important concept for any kind of time sequences you're dealing with. But another topic that comes up at the end of today's lecture is what's called as attention models. How do you get a neural network to pay attention to certain important things, right? I mean, it's very difficult, even as human beings, to pay attention to everything. But how do you pay attention to some important points? For instance, when you're trying to make a machine translation, you need to pay attention to the right words to get the translation right. So they introduced, the machine translation people, the neural machine translation people introduced the idea of attention. And attention is not only important for human beings, but for also in other applications of deep learning, other than natural language processing. Attention is also important in computer vision, and it is important in all areas. So it is a central concept, but it was all introduced by researchers on natural language processing. Okay. All right. With that preamble, let us begin to look at the slides on natural language processing. And I will see if I can bring that up. Okay, bear with me while I figure this out. I'm trying to share the screen now on the PowerPoint. So share screen. Okay, there's the PowerPoint. And share. Okay, hopefully that's working now. And you're able to see the slides on neural machine translation. Okay. All right, so where does this fit in? Neural machine translation fits in among topics in natural language processing. It's topic number 5 is neural machine translation. Last of the topics, we already looked at Engram models. We have looked at neural language models. Engram models was about capturing probabilities using sequences of words, 1, 2, 3, like that. And then neural language models was about embedding. How do you take words and get a vector representation? And high dimensional outputs was the topic of last Monday, where we spoke about the interesting topic of how, if you have a large number of outputs, how does a neural network deal with it? That can happen in any kind of neural network you're trying to design for a supervised learning problem. I have not hundreds, but thousands or maybe 10,000 or 100,000 possible classes. Combining neural language models with engrams is a topic that I have slides on. I thought it was less important than moving on to neural machine translation. So those slides are there. I welcome you to take a look at it. How do you combine embedded models with neural language models to get higher performance? You can look at it as a classifier combination problem. And today's topic is neural machine translation. And within neural machine translation, the topics here are why this topic of machine translation. I already mentioned a little bit today at the preamble, but it's a very interesting topic and a very valuable topic to look at. And we then look at a simple approach to machine translation based on multi-layer perceptron. And that has done quite well using a neural network to perform machine translation in a simple way. And then a more sophisticated way was using a recurrent neural network approach to machine translation, which did much better. And then we move into this whole revolutionary area called using an attention mechanism and aligning pieces of data. Today, I will just, at the end of today's lecture, introduce this attention mechanism, but we'll have a full lecture devoted to this topic next Monday. Okay, so let's begin with an overview of machine translation. So what is machine translation? All right, here is an example of machine translation. And let's say we have the source language. We use some terminology here. We call it as a source language and a target language. Our source language, let's say, is English. And we have here a question that we would like to translate it into a target language. The question we have is, would you like coffee or tea? And the target language, I chose here 7 languages, which, in my very biased opinion, are the most important 7 languages of the world. All right. First is French. You would say, voulez-vous du café or du thé would be the translation. So we'd like to generate that in French. Or we could translate it from English to German, and you would say, Möchtest du Kaffee oder Tee? So that would be German. And if we want to translate it into the language of Bangalore and Karnataka, in Kannada, you would say, Nivu Kafi Athva Chaha Bayasuvira. I've written that in English below in case you cannot read Kannada. And then in Hindi, we would say, Aap coffee ya chai pina pasand karenge, would be Hindi, which I can read. And if you can't read it, you can look at the purple letters, which gives you the transliteration. And you can translate it into Tamil. I cannot read the Tamil script, but in English that would go like Ninkal kapi alattu tenir virumpirkala, right? That would be Tamil. And I wonder if it was colloquial Tamil or very pure Tamil, but that's Tamil. And in Japanese, you would say kohika ocha ga ide suka. And in Chinese, you would say ni yao cafe haishi cha. Anyway, these are the 7 languages into which we have translated, would you like coffee or tea? And I was just looking at these translations, and I found how coffee is exactly in English and Kannada almost the same. I guess German also, café. In French, it becomes café, and in Hindi, it's kofi, and kapi is in Tamil, and coffee in Japanese is kohi. Kohi is coffee, and in Chinese, it seems to be cafe. Okay, it all sounds pretty much the same in all these languages, coffee. Tea is interesting. We'd say te in French and tea in German, and in Kannada, you would say chaha. That comes from chai. There are 2 different distinct words, it seems like. Tea and chai are 2 different words for the same thing. Chai in Hindi, and then we have, interesting, in Tamil it says tenir. I never knew that. Tenir sounds like tanir means cold water, right? But anyway, it's a different word. Tenir is tea in Tamil. And in Japanese, it would be ocha, similar to cha. And in Chinese, it is cha. I guess it's originally a Chinese word. Cha, tea came from China, so it's probably cha is the right original word. And coffee, probably it was Karnataka where it came from. So we have the word coffee or coffee, and that's what adapted by everybody. So anyway, those are the words. So anyway, here is the task. Translating from English to any of these languages. That's just a translation task. It's not machine translation. So machine translation's task, or MT, is to read a sentence in a natural language. We just saw some natural languages. Those are not formal languages like Python or C or some. Those are formal languages. Whereas natural languages are these kinds of natural languages people use. So we read a sentence in a natural language and emit equivalent sentence in another language. Our machine translation is to develop a computer program to convert source text to target text. So we are using specific terminology, source and target. And using a machine learning approach to this problem would involve taking examples like French sentences. If you'd say on ya means in English, it would mean let's go. In French, you would say pour la première fois is in English would be for the first time. Or non je ne regrette rien is no, I do not regret anything in English. And après la pluie, le beau tempe would be after this rain, nice weather. Okay. So a machine learning approach would be to take a whole bunch of French sentences and given the English translations to learn what's going on here. It's all going to be, of course, a probabilistic mechanism, which is going to figure out all kinds of relationship between words and how to even figure out meanings and so on. That's the task of machine translation. And this is just a slide on why this machine translation is important and what is happening. Okay, today neural machine translation is eliminating demarcation between human and machine translation. It has become pretty good. And it has improved human productivity. So people can always quickly look at translations into their native language to understand what is being said. And they will also allow making machines more accurate going forward. Many of the technologies developed, as I mentioned already, are from here and being exported to other topics. And there are a whole bunch of machine translation engines. Do you really need to do it from scratch? I suppose a lot of them are available for any pair of languages. You can imagine there would be pairs of languages. If there are 150, 180 common languages, then you would have to do 180 choose 2, which is about the order of 3,000 or 4,000 machine translation engines you need. And many of them are already available. You can click on Amazon Translate that does this for you. I guess they try to sell products all over the world. Crosslang, DeepL, Google Translate is another translator, Microsoft Translator, Unbabel, Watson, that's an IBM product, I imagine. So almost all the major companies have a product in machine translation. And they're all using this kind of technology, neural machine translation. Of course, we look at a few simple ones and then more involved ones. The simple ones are the early models. And then the later models are much, much more sophisticated. But we want to begin to understand it, we begin with the early models. So you can think of how machine translation is to be accomplished. You can say that it involves a proposal and an evaluation approach. And a proposal component suggests translations. And you could simply, for instance, get a translation of every word, like, what is coffee in that language, kohi or so on. And then how do you translate tea? You would say, well, that's cha. And you could simply literally translate words and put them together in a sequence. And so many of those translations will not be grammatical. Many languages put adjectives after nouns. So you might say, when translated to English, yield phrases such as apple red. All right, so apple red. And a proposal mechanism suggests translation variants, ideally including red apple. So one variant might say the translation is apple red. And another mechanism says, well, that doesn't seem to be the right order. Put adjective before the noun, and you put in red apple would be a variation. So you would have many of these variations. And you can say, well, we need a method, a language model, if you will, to evaluate the translation. And that assigns a higher score to red apple than to apple red. All right. So you can think of it as proposal generation and proposal evaluation. And say, okay, so we will go with a more probable or one with a higher score, which is the red apple is the right translation. So in machine translation, as I mentioned earlier on, it is an old topic. And very early models did not use probabilities, and much later came the ideas of using probabilities. And the first probability model that was used was Engram models. We spent a lecture on engrams, where we look at the probabilities of words and word pairs and word triples and so on. And those are called Engram models. So given the probability of 2 words or 3 words, one can calculate the probability of any sequence of words by appropriately multiplying the trigrams, and you would get a probability for that sequence. And the problem with that Engram models was that a lot of the combinations never occur in English. Some combination of 3 words. There's so many combinations you can think of are totally ungrammatical, so they don't occur at all. 0 number of times they occur. So the probability becomes 0. And for that reason, they came up with slightly improved methods called back-off Engram models, which allows you to back off by 1 word and use that to calculate the probability of, say 3 words from 2 words and so on. And that's an improvement. And there have been other improvements called maximum entropy language models, which also attempt to improve the Engram models. And all of these models go about reporting the probability of a natural language sentence. So what is the probability of this compared to the other? And so this is how things were. And Then neural networks came along with their popularity with embeddings and so on. And the first neural networks upgraded the language models. They simply said, well, instead of calculating Engram probabilities, let's have a neural network compute the probability. And so that was the first thing. But that wasn't really the best use of neural networks. And neural networks then went on to calculate conditional models. So while the traditional language models simply report the probability of a natural language sentence, and the model can now be extended to become conditional. That is, what is the probability of this sequence, not in absolute terms, but given a few words or the context in which it is occurring, what is the probability of this sequence? Which makes sense. In English, context is extremely important. So if I ask you what is the probability of some pair of words, red apple, you can simply calculate the absolute probability, which we call marginal probability, among how often that red apple occur compared to all other pairs. It's not as useful as in the context of eating a red apple. Right? In the context of eating, now we can say red apple makes a lot of sense, or eating pizza or something like that. So there are so many other possibilities, but it will become a conditional probability. And we refer to the word eating as a context C. And now we want to compute conditional probabilities. So that is where things got a little bit more sophisticated. And the people from machine learning came along and said, we can come up with a successful conditional model. And it produces a conditional distribution given context C, where C is a single variable or a list of variables. It could be a single word like eating, or it could be a string of variables. So this particular, referred to as MLP, stands for multi-layer perceptron, scores a phrase T1 through TK. These are the phrase, so many words in the target language, given a phrase S1 through Sn in the source language, by estimating PFT1 through TK given S1 through Sn. So it's a whole sequence. And it beat the state of the art in statistical machine translation benchmark. So it was a particular system that was developed. And they were always interested in this topic. So there were benchmarks and competitions. And this something based on multi-layer perceptron beat all the simple Engram models and so on. But the disadvantage of this multi-layer perceptron model was it required inputs to be processed be of fixed length. So it is so many words of a given length. And so limitation on that, not variable length. So then came along recurrent neural network models, which were an improvement over the previous ones. It provides the ability to accommodate variable length inputs and variable length outputs. So I give you some string of a given length and produce a string of another length. And the RNN, or recurrent neural network, it represents a conditional distribution over a sequence given some input. So it takes a fixed length vector X into a distribution over sequences Y. This looks like a complicated diagram. It is actually borrowed from our earlier discussion on recurrent neural networks. So we have an input X here, and we have what was the hidden values of the previous word, current word now. This is the embeddings we're talking about. And this is for the next word that might be coming up. And here's the whole sequence for all their embeddings. And we're at the current state X here. And what these things show here is the hidden values are going to the output values. And then we are comparing the output values during training phase. L stands for loss. And Y would be the output. And the output is compared to the input and to the value produced by the output by the loss function, and that's for the purpose of back propagation. So similarly, we are doing H goes to O to L, that is hidden to output to loss, and this is the supervised output here that's being compared to compute the loss function. And then we are in turn using these values back here, the output values, to predict the next value over here. So now we are using an RNN in the sense, if you recall, we are unpacking or unfolding from one. So you can think of this pathway as one feed forward network, and that is being unfolded over time to create these different sequences. And there is a relationship between them, between the hidden units. And then the outputs are also being used here. And this kind of a model would be able to do things like, this is a screenshot from a company called the Allen Institute for Artificial Intelligence, AI2, founded by Paul Allen, founder of Microsoft. And their product here shows if you type in the cat sat on the, it's able to give a probability for the next word that is mat or what have you. It gives you different probabilities for different words. I just put this in because it shows that there is a probability distribution associated with it, given all this background here. So that's just for one word, and we're calculating the probability with a sequence here. So RNN was doing this. So in a sense, in machine translation, we are taking a sequence of inputs and outputs and predicting the next word, taking into account what was predicted. And that's the kind of model it was. And the RNN model is also being summarized here. It's referred to also as an encoder decoder framework. We have a source object shown in the diagram, which is a French sentence. Or this idea RNN model can also be used with images too. Let's just focus on language. So the source object is a French sentence. An encoder produces an intermediate semantic representation. So it is mapping it into something, a sequence of numbers, if you will. So these are real numbers. And that is being output into an English sentence over here. So we're going from source to intermediate to output. So one model reads the input sentence and emits a data structure that summarizes the input. We call this summary context C, maybe a list of vectors or a vector or a tensor. The second model is an RNN. It reads a context C and generates a sentence in target language. So this was the next stage. So keep in mind the sequence of improvements here. I think it's still worthwhile. You can say, why do we need to know any history? But it shows the logical thought process to keep in mind when we go on to more sophisticated models. So first we began with syntactic methods, then we went into an Engram approaches. Then we went on to replacing those probabilistic models by simple neural networks. And then from simple neural networks, we are now moving on to recurrent neural network models here. And the recurrent neural network model again is an encoder decoder architecture. And you can say it is to map a surface representation. This is an old terminology of natural language processing. They talk about surface representation. So you have a concept and in your mind, and then that becomes a surface representation. What you type actually might be a approximation to the real concept. But anyway, there is a source. And then when you translate that into another language, you're saying, well, there must be some intermediate representation we can generate. And this used to be called as an interlingua. Interlingua is some representation in maybe some intermediate language which captures the concept well. And so we go from a source language, so a source sentence in some language, we go to an intermediate semantic representation. And we take an output, which is again a source representation. For instance, we could go from English to intermediate to English again. It might not turn out to be the same because there is some loss in the intermediate representation. But we could also go from French to English. So uses output of encoder data from one modality to another and provides as input to a decoder of another modality. So mapping from French to hidden representation and from hidden to English. The early folks in natural language processing were trying to figure out what could be a good interlingua. And they had a hard time saying what is the nature of interlingua, and they were thinking of things like transformational grammars and so on. But these neural networks figured it out and say, well, we can just represent these things in terms of numbers real numbers, and you have an infinite set of possibilities. Keep in mind that when I say a number is between 0 and 1, I am specifying an infinite possibility, right? 0.11 is different from 0.12, or 0.135 is different from 0.1357. So you have a lot of possibilities in real numbers, even with one number that lies between 0 and 1. And we got all these hidden units that represent all kinds of numbers. So you can get a, a large here, a huge number of possible representations for anything you may want to represent. And so that is the secret of all of this, of mapping into numbers, real numbers here.
Sir, I had a question here.
Yeah. Let's see, Sumant Kumar, you have a question? I'm trying to see whether I can bring you up here into video. All right. Okay, fine. Go ahead. Maybe you don't have a video feed there. Okay. Oh, there you are, Sumant. Yeah, I can see you. Okay, how are you? Yeah.
Yes.
Where are you calling from?
Yes, sir. I'm from Bangalore, sir.
Okay, fine. We're all Bangalore talking to each other. Okay. All right. Go ahead.
So my question was, here we are trying to encode from different languages. So if we have two different languages, we encode them. The encoding would be different for the two, or would be the same?
See, you look at this diagram right here in front of you, right? So there is only one intermediate representation. So we have trained it from French to English. So it has figured out how to come up with this intermediate representation between French and English. So the pair of languages is given ahead of time. So this is about French and English. And so there is a certain.
So this is specific to the input and output. Okay, got it.
Right?
So it is dependent on the pair.
For every pair of languages, you'd have to have a different representation, right? You can't say I'm going to use the intermediate representation to go from, let's say, English to Hindi or something like that. You can't use the same one.
Right? I thought there was a single language, then we can use that as a universal.
Yeah, that was the idea. The natural language folks had that idea that maybe there is some hidden language that all of us use, all human beings use. We just need to discover what that language is. Actually, even I had a paper about 30 to 40 years ago on how Sanskrit could be a interlingua. Sanskrit, I mean, it sounds a little fantastic to say that, because in Sanskrit, you have, we have order-free representations and, vibhaktis and all that, which seems to capture the idea of the concept much better than any other language. In English, everything is dependent on order of the words. In interlingua, would just have the concept for the word, so on. There might be something like that. We were all looking for this.
Has to capture the context only, like.
Yeah. Well, in this case, context is a particular sentence, right? So it has got, then we'll deal with what about the context of other sentences, or a whole paragraph, or a whole book, right? So those are all complicated things, and they have good solutions to it. That's the amazing thing now. And we are not here only talking about like one sentence. So, so that is the kind of representation, all right? So anyway, this idea, encoder decoder architecture, has been applied successfully, not just to machine translation.
I have a question.
Let me just finish that thought here, machine translation, but also to caption generation from images. There are very sophisticated systems today that you just take a picture with your camera, and that generates a description of what it is that you just took a picture from. That's called caption generation from images. Okay, all right, go ahead, ask your question. Who was the one? Ram Kiran, you're asking the question? Yeah.
Right.
Yeah, go ahead.
My question is, how will you get input data sets for this kind of model? Like,
yeah, I gave you an example of French to English, right? So you would have people translate from English to French, and I'm sure there are lots of examples of this already. For instance, there are journals, right, which publish a paper in 2 languages, or there are newspapers. And okay, newspapers may be bad because they're using different language, different concepts, but there are plenty of data sets of translating from one language to other. For instance, you could look at transcriptions of speeches, maybe. in one language and another language. So you would have
Sir,
a, let's say,
it's
pretty
okay if
disparate.
you take the popular languages like French or English.
What's that?
It's a popular. These are popular languages in the world.
Yeah,
Suppose we want to do it in our some state level languages in India, let's
yeah.
say Kannada.
Yeah,
In that
you know,
case,
I alluded to a half a dozen commercial products that are available. It's just remarkable how many pairs of languages they have captured. You know, and of course there is always room for more. I think the world's languages is not just of the order of hundreds, maybe of the order of thousands. In which
yes,
case
it's
there is
200.
always room for more research for some pair of languages it doesn't exist. And you would want to do a research project to do machine translation. And then it's a legitimate question, how do you get the data set for it? And if there are those rare languages, maybe it's going to be hard. There aren't transcripts available for rare languages. So creating the data set will become the biggest task. They say in machine learning in general that the future of machine learning is going to be in the data, and to curate data, saying, okay, here is the data set and here are the transcriptions of in two languages, and make it available. So that is the challenge for a lot of those. But
Sir,
the state of the art
one
is
question.
quite remarkable where it stands today. Okay. Yeah. All
So
right.
one question
So
that intrigued me is like I was going through an online research on these language models only. What they want to fit is the language of Mohenjo-daro and Harappa. They have symbols of leaves, bullock carts, some pots or something. They do not really know what is the real thing,
yeah.
but they are trying to fit based on it's an unsupervised learning setting. Based on the settings, they are trying to get the inference out of it. So I'm thinking in those grounds where you need not actually require a supervised setting. Only we require the relative, like all languages will have an inference coming out of it. So we can use that as some kind of initial point for translation.
Yeah. Yeah, those are all, I mean, that would be a highly interesting project. But you may want to look at, how others approach some of these problems. The famous one is the Rosetta Stone, right? You know about that, right? The Rosetta Stone was the first time they discovered mapping of the Egyptian hieroglyphics. What are these? That's what you're talking about. Those in Harappa and Mohenjo-daro, you got those symbols of the bull and all that. Same kind of thing in hieroglyphics. So they found in one stone, whatever message was being conveyed was given in some 2 or 3 languages. And he said, here is the Rosetta Stone, which shows the translation between the hieroglyphics. I don't know what other languages they had, maybe Latin or something like that. And they were able to figure it out from a small sample. I found a similar thing. If you go to a temple in Tanjore, not too far from Bangalore, in the Brihadeshwara temple, I found a stone there. They pointed out this is the first time they were able to relate the symbols. I think Brahmi or something like that, one of those languages, to Tamil or something like that. So they were able to find a pair. It says, wow, this is the clue to what the mappings were. So, I mean, those are very small samples. And similarly, if you have to do that for Harappa Mohenjo-daro, maybe there isn't a Rosetta Stone available there. In which case, what you're saying may make sense to do, I don't know, unsupervised learning to see how often these symbols occur, and you look at their relative frequencies. It's an interesting research problem. So anyway, those are all kind of tangential to what we're trying to do here, which is dealing with very practical common languages. And how do we achieve it? So once we have a solution to these problems, maybe we can foray into those things. All right, fair enough. All right, so let's go on to RNN encoder decoder. So this diagram again shows the encoder model on, in this figure here. The encoder model is a sequence x1 through xt, And this is a sequence, and that sequence is being mapped into a context C. So you see, these exponents could be embedding, 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 right? We know how to do embeddings. Every word becomes a 300-dimensional vector. And this sequence is now being mapped into some vector again here. How could you map all of these? Well, that could be another, it doesn't have to be too huge. Whatever the size of this context vector you want, that captures what was all in this sentence. And that context is going to the decoder, which is producing the outputs y1, y2, yt this way. And we are going from, we generate the output from the input, and that is being taken to generate the output over here, and that output in turn goes over here, and the state is being used to generate the output. So we are going about generating a sequence, but the important point here is the context is modeled by C. So the RNN encoder decoder, to generate the output sentence, conditional source sentence, model represents entire source sentence. And so the context is taken into account, the input word is taken into account when generate output words here, right? And so early models able to represent individual words or phrases, and neural models learn a representation in which sentences with same meaning have similar representations regardless of whether they were written in the source or target language. We're going to be spending some more time when we deal with attention models to distinguish them between encoder decoder models. Let's say first look at encoder decoder sequence. So then comes this whole idea of attention, saying using a fixed size representation to capture all the semantic details of a very long sentence of 60 words is very difficult. Let's say we have 60-word sentence or a 60-word paragraph, and that is the context. So we are saying context C is a fixed size representation that tells you what is the context here. And although it can be achieved by an RNN trained well enough and long enough, a more efficient approach exists. And this says, how can you represent a very long context? And that's where this whole idea of attention comes in. So we're going to be spending a whole lecture on attention. But today, my goal was just to introduce the idea of attention and look at most of the details next time. So the attention mechanism, what is it we want to get a sense for? It is to read the whole sentence or paragraph to get a gist or the context, and then produce translated words one at a time, each time focusing on a different part of the input sentence. So we're saying we got the gist. So you have read a long sentence and we know what it's talking about. Now we say, okay, let's do the translation. So you know the context in which all this is happening. And the attention mechanism is used to focus on specific parts of the input sentence at each time step. So we are going to translate these words. It's not going to be literal. So we're going to be looking at what does this word mean in this context. So I have an example in the next sentence, next slide. Supposing you had a sentence, she is eating a green apple. So there is some correlations happening between these words. So it is all about how we correlate words in even one sentence. So when we see the word eating, okay, she is eating, we expect a food word soon. And so after eating, we are getting the word green. Green describes the food, but the word eating goes along more with apple. So what are you eating? You're not eating green, you're eating an apple. So for instance, for the last word, you can say, well, she's eating after green, we could say chair. Green chair would go along. Green chair is fine, but then chair won't go along with eating. So there is a higher probability for that last word being apple than chair. Although green agrees both with apple and chair. Green apple, green chair. But eating only agrees with apple and not with chair. So what we're saying is there is a high attention to the word apple from the word eating. And there is a lower attention from the word eating to the word green. So there is a differential amount of attention going on here. So we say attention in deep learning is a vector of importance weights. So in order to predict or infer a word in a sentence, we estimate using the attention vector how strongly it is correlated with or attends to other elements. So the last word is being attended to more by eating than by green. All right. So this is the idea that there is something going on here, that the attention between words is not all equal. It is specified by this concept of attention. And of course, how does the system know that eating goes with apple? Of course, you need to have a large enough training corpus that has got lots of examples of these kinds of things. This is not just for machine translation. Attention is a concept that transcends machine translation. It applies to all of natural language processing. It applies to computer vision. It applies to anything you can think of. Attention comes into play, that everything is not equal in terms of context. Here is another example. An application of machine learning or natural language processing is in sentiment analysis. So we are teaching a program to figure out whether a particular review is good or bad, right? Some gradation here. So here is an example review. Somebody was doing a review. I suppose this is a review of some restaurant, and they happen to be eating something like pork chops or something. They're saying they wrote pork belly equal to delicious. They wrote scallops. This was the review. This is kind of a very abrupt type of review. Pork belly equal to delicious. Scallops, question mark. I don't even like scallops. And these were amazing. He typed in like that. And then he wrote fun and tasty cocktails. And then the next one was not even grammatical. Next time I in Phoenix, I will go back here. And then concluded the analysis by saying, I highly recommend. So this was what was being given in the training data. And this attention mechanism was being fed into an attention mechanism system, that it learns that out of these 5 sentences, the first and the third sentences, pork belly equal to delicious, and these were amazing, are more relevant to the final conclusion, highly recommend. And furthermore, the words delicious and amazing within those sentences are more meaningful to determine the sentiment of the review. So we got all these words, and there's a conclusion that there is a highly recommend here. And not all words are equally important. The words that made highly recommend possible there were words like delicious and amazing, and the rest of the words were not as relevant. So an attention model captures this importance in this context, so that in the future, when it's supposed to look at reviews on its own, and I suppose the task would be to get the program to evaluate reviews that are coming in, what it thought of the reviews. Was it a positive or a negative, in what way, and so on. So that is, so this is of course a training data. This is like a supervised training. You're saying that's highly recommend. Okay. So the next couple of slides is just a very first view. We're going to spend much more time on this attention mechanism, but I want to convey the simple idea. What is context? Context with that attention mechanism is a vector, just a vector. Okay, it's like we talked about 300-dimensional vectors. It could be another 100 or 200-dimensional vector. It's a weighted, what is it? It is a weighted average of feature vectors ht and weights alpha t. So there are these feature vectors ht. What are these HTs? The HTs could be the embeddings of words, or they could also be the further up layers. It could be embedding of embedding, that kind of a thing. So these are the hidden units, and that represents a whole sequence earlier on. And these alphas here, alpha t minus 1, alpha t, and alpha t plus 1, as you can see here, we are taking these alphas and this crosses multiply. Alpha multiply h to give this number. Alpha multiply h to give this number. Alpha multiply h to give this number. These numbers are going up here to c, and we are saying plus, with all these added. So a context vector is a weighted average of feature vectors H and weights alpha. That's all it is. Okay. It takes into account all these things that are coming in, and it also attaches some weight. So that becomes the key point. What are these weights? How do you get those weights? Like we just saw, she is eating a green apple. Somehow the way, when we are trying to predict the next word, the apple, we are saying there is more emphasis on the word eating rather than on green. And those would correspond to these attentions, the value of this importance. And that is what goes on in attention mechanism. So what are these weights? These weights are themselves are a very interesting problem. We'll just say this is what they are. Weights alpha t are produced by the model itself. They're usually values in the interval 0 to 1, just a number between 0 and 1, like a probability, and are intended to concentrate around 1 ht so that the weighted average approximates reading that one specific time precisely. So these are all at a particular time instant. The context, these values here, one of them is kind of high, saying, hey, this is the word that is important for you. So it is saying that is the importance of this word, or this word here, that's important for you. And how do you produce them? That's the intriguing problem. Weights alpha t are produced by applying a softmax function to the relevant scores emitted by another portion of the model. So we need to spend some time figuring this out. And it turns out some kind of logistic regression is used to figure out what these alphas are. So that is a whole sub-machine learning problem to learn these attention weights. Anyway, we'll keep that for another time. But we'll just look at the overall mechanism. Somehow we got these alphas. So, and these attention model can be trained. The attention mechanism is actually more expensive computationally than directly indexing the desired edge. Couldn't you just directly take these edges and take it up here without the alphas? But directly indexing cannot be trained with gradient descent because the edges may correspond to the current words. Because we're not talking about something all pre-trained ahead of time. We're talking about the input is this sentence, she is eating an apple. And you got to use whatever knowledge you had earlier on to process this bunch, and the context corresponds to this context, not the context of all sentences that we have seen in the learning phase. So the attention mechanism based on weighted averages is a smooth differential approximation that can be trained with existing approximation algorithms. So turns out this is amenable for training this type of a model. And training, of course, becomes an important issue. And so the three components of attention. So attention has three components. One is about reading, one is about memory, and another one is exploitation. So an attention-based system has three components: a process that reads raw data and converts them into distributed representations. Those are the embeddings we know about, with one feature vector associated with each word position. That way, that's an easy part. So that is just getting the embeddings for the words. And a list of feature vectors storing the output of the reader. And this can be thought of as memory containing a sequence of facts which can be retrieved, not necessarily in order. And a process that exploits the content of the memory to sequentially perform a task at each time step, having the ability to put attention on one memory element. That third part is the critical part. The first two are simply saying a raw data and then the embedding, and the last part is to exploit it properly. And it's the third component that generates the translated sentence. So we're going through some embedding into the output. And word embeddings between the representation. So now we have an embedding word in the source language, an embedding of a word in the target language. And these alignments are useful to compute cross-lingual word vectors and to training larger data sets. So this is just a small point that's being made, that when you have huge data sets of translating between English and French, and you're aware of all kinds of cross-lingual word vectors, and so relating word embeddings becomes useful. My last two slides for today's lecture are just very general statements. And what is the importance of attention models? Okay, when did this come around? Attention models was first introduced for machine translation by an author, Bahnanau, 2014. So it's about 5 to 6 years ago when this whole idea of attention models was introduced, but how we can have different weights for different inputs while we are doing a task, a sequential task such as natural language processing or machine translation. And it became a remarkable tool for NLP, natural language processing, for statistical learning more generally, for speech, for computer vision. All of these started jumping in on this topic. And then we can ask, why is it that attention models advance so much? Reasons for attention models. They started to achieve state-of-the-art in competitions for tasks of machine translation, question answering, sentiment analysis, part of speech tagging, another NLP task called constituency parsing, dialogue systems, and so on. So whenever you brought in this attention model, you started doing exceedingly well. And it turned out these attention models have advantages beyond improving performance. Well, fine, they won the competitions. They improve the interpretability of neural networks, which are otherwise black box models. What we're saying here is notorious, neural networks are notorious, right? So what is this? A black box. You can't tell how it did it. It says it's able to say it's a cat. And you ask, why did you say it's a cat? It cannot explain itself. Similarly, why did you translate it from this sentence to that sentence? Can you give any explanation? And it says, yes, because I put more emphasis on eating. That is why I chose apple instead of chair. She's not eating a green chair. She's eating a green apple. So why did you get? So the reason is I was paying attention to eating. So it turned out these attention models are useful for explainability. And they also overcome challenges with recurrent neural networks. Recurrent neural networks, if you give long enough sequences, it'll learn all the vectors that you need, but it becomes pretty long. And attention model seems to capture that in a nice summary form, right? Okay, so that is my prepared lecture for today. And
Sir, I have a question.
yeah. Before I wrap up, I was just going to say that we're going to have a full lecture just devoted to attention models. You want to look at it, that slide, because it is such an important topic. I think it's really important that we study it very carefully, generating the alphas. And then again, we start again with the encoder decoder model and to figure out all kinds of details about it. So that's what we're going to do. Okay, with that statement, let me take your questions. Shreya, you have a question?
Yes, sir.
Okay,
Sir,
I'm going to see if I can get you online here. Okay.
Yes.
Yeah. Okay, go ahead.
Yeah, sir. My question is, in LSTM also we are like with the input gate. I mean the forget gate, and they are deciding how much to contribute from the previous states, right? So this can be. I mean, what is the difference between bidirectional LSTM and the attention
Okay.
network? Because
one of the two concepts you brought up, one is old and the other one is new. And I'm talking about something in between here. LSTM were an improvement over simple RNNs, right? So the RNNs, okay, that's a very good question, because LSTMs can remember old stuff, which RNNs found it hard to do. And so people did machine translation saying, okay, let's replace the simple RNN module, which is just an ordinary neural network module, ordinary neural network cell with an LSTM cell, so on. So, or GRU, some variant of that. So they can do much better. When we say RNN here, we are meaning it's a simple RNN, or it could be an LSTM type of RNN, or it could be a GRU type of RNN. All of them are being captured here. And then they found that once they invented attention models, says, okay, those are going to do much better than whatever LSTM you could possibly use. So attention kind of is replacing all of that. And then we move onwards. Towards the end of the next lecture, we're going to be looking at a particular attention model for NLP or machine translation and these kinds of tasks, which is called bi-directional attention model. And there is the state of the art, as far as I know, is called BERT, right? BERT uses, B stands for bi-directional. And it also uses, the T stands for transformational. So there's one more concept we need to do before we go to BERT. So we have now gone from simple RNN to LSTM to now RNNs, the encoder decoder model. All right. So we got to that point. So the next concept we need to look at is, what is this transformer model? It's a kind of attention model. And then after that, the final thing we're going to look at is this BERT, which is apparently an unbeatable system that's available from, I believe, Google. And people just are, directly using it. They've done all the training for you and all these massive texts and so on. And how does it do it? It is using this version of attention model called transformational. It's even bi-directional. Okay, again, to get back to your question, okay, LSTM got replaced by these kinds of things, attention models. And your question was also about, what is this bi-directional? Bi-directional is simply, instead of looking left to right, what if I looked left to right and right to left as well? Instead of predicting the word apple using eating, can we go the other way around, looking at apple and say, well, okay, eating seems to, maybe apple would be equal to green and eating, either could go. But it is bringing some more contextual knowledge. So we always find this when we're reading something, we might not understand something, but when we read something later, it says, okay, that's what that originally meant. So we can go back and figure out what we didn't understand by looking at the later concept. So these bi-directional methods capture that notion as well. All right. So anyway, good question. And so it is in the past as well as in the future. Okay. Yeah.
Sir, in the attention model also, I mean unidirectional attention model also, we are doing almost the same similar thing, right? We are taking the weighted average of some previous sequences and of some next sequences, right? So
yeah. So you're saying LSTM does the same thing? Is that what you're saying?
Yeah, bidirectional LSTM is.
Yeah. Forget about bidirectional. That is just a variant of it. We have both unidirectional and bidirectional, both for these kinds of attention models, as well as for LSTM. So let's say you're saying LSTM captures the past information, and whereas attention model also captures the past information. What's the difference, right? That's your question.
Yes, because it is also, there is the alpha T, alpha is the way.
Yeah, that is right. Hidden. Yeah, you can see there are so many more parameters involved here than LSTM. It is kind of giving some variation. It is averaging all of them to sum to one, right? So these alphas saying unequal type of weights to different things in the past, whereas this LSTM was a fairly simplistic mechanism as what to remember, what not to remember. And this is giving a fine gradation. So in a sense, it is giving you different weights. Maybe that is the main reason why attention mechanisms are more powerful than LSTMs. Okay, so that's a good question. I don't know whether there are nice discussions about that comparison, but I'm just speculating that is the main thing. Okay.
Okay.
All right.
Okay, sir.
All right. Any other question?
Yeah, I have a question.
Okay, Selvi. Oh, hi, Mrs. Selvi. How are you?
Hi. Yeah, fine. Thank you, sir.
Let me introduce you to the class. This is Professor Selvi Selvan. She's the head of the Department of Communication Engineering at MS Ramaya College. Okay, welcome, Selvi.
Yeah, thank you, sir. I just wanted to ask this encoder decoder structure, what you were talking about. is it same like the auto encoders which we talk about, or is it different from?
Oh, okay. Okay, good question. Is the encoder decoder we're talking about same as auto encoder? We haven't covered auto encoder in class yet, but
Okay, okay.
yeah, but that's okay. That's okay. That's a good question. In auto encoder, what we're trying to do is come up with a representation. You know, we're
Yeah,
saying
correct.
here is an input, and we want to take this complicated input and come up with a compressed version of it, saying here is a representation of your input. And what kind of representation is it? Well, we should be able to decode it so that we are able to reconstruct the input as well as possible. That's why it's called auto. Auto encoder means take an input, produce the same thing as output, and in the
Okay.
process you compress it to something. So, and that becomes an essential representation. So why is the auto encoder useful? All it is saying, compress it and decompress it. It's something
Okay.
like you know, when we
JPEG
compress an
or
image,
something.
right?
Yeah,
When we are
JPEG.
using data compression,
Yeah,
we could say, well, in data compression, what do? We simply saying, instead of taking so many megabytes, compress it into a smaller number of kilobytes, and then so that at the receiving end, we simply decompress it and reconstruct it as good as possible. The difference between the ordinary data compression and encoder decoder and auto encoder was that, well, it is specifically constructed for some class of images or objects, and not in general. It's not MPEG or whatever compression you have. It is only for cats. It's only for dogs, whatever images you have, because it's trying to
correct.
figure out what is the essence of a cat, what is the
Yeah,
essence of a dog. So that
yeah.
is the representation that goes on with auto encoder. I was just giving that tutorial. I know you know that topic, but my class hasn't looked at auto encoder.
No problem.
I was just telling them
Yeah.
what is an auto encoder decoder, and it is useful to learn a representation, and it has got
Okay.
all kinds of other uses. Here
But
we are
we are
talking
doing that.
about a representation specifically for natural language, and
Okay.
this representation is something that is useful, say, for machine translation, and for a particular purpose here. And in a standard autoencoder decoder, we don't have a specific purpose as such, whereas in this case, we are doing an encoder decoder. It's a very intriguing thought you have, that there is some interesting similarity between the encoder decoder of natural language processing and an autoencoder concept, which is largely used with images. And there also you have encoder decoder. Only these things is these criteria are different. Here specifically, we are talking about weighting specific sequences of words and so on. So I think it is more about the peculiarities of the application, but the similar ideas come about here, that the representation here, we call it as an interlingua, the context, and there we call it as the hidden representation. So
Yeah, you got.
so yeah, that's all it is. So there is a strong similarity between the two. Good point.
Yeah,
Yeah,
yeah. Thank you, sir.
yeah, very nice. Nice to have you in class.
Yeah, thank you,
I
sir.
know you teach deep learning, and
Yeah,
you
yeah. It
yourself
is.
teach it, right? Autoencode and so on. But I tell you,
Yeah,
this
that's.
topic, NLP, it's a lovely
Mm,
topic, and it
yeah.
captures so many different things all about deep learning. And if you
Mm,
want to look at one application that brings everything alive, it is this one. Okay, good.
yeah.
All right.
Thank you, sir.
Yeah. Any other questions?
Somebody else had a question.
Yeah.
When I was starting, somebody else started. Yeah.
Okay. Himanshu, you have a question?
Yes,
Go ahead.
sir. How are these attention models beneficial in computer vision?
Oh, how are they used in computer vision? Okay. So, we need to have a whole lecture on that topic. We're going to be continuing with just attention models and language for the next lecture. But you can think about it in computer vision. There is a lot of stuff. This is a borrowed concept. It was not a concept invented by computer vision guys. It was invented by NLP guys. And the computer vision guys came along and said, oh, we could use that idea, that while you're trying to recognize something in an image, you are taking into account the context of, let's say we have a picture of a photo of a dog, let's say, and the dog happens to have these pointy ears. Uh, on top. I suppose dogs have different kinds of ears. Some dogs, right, like an Alsatian or something like that. It's got these pointy ears. Okay, you recognize the ears now and says, oh, there's got to be a dog's face coming up soon. So attention can be said. We use context in one part of the image to predict another part of the image. So that can be useful there also. And so that's the basic idea, that just like predicting the next word can rely on a particular word. And why do you want to predict a word is because we're trying to guess what is the next word in this translation or in this speech recognition. So all of them, we're always trying to predict something. And same thing in image recognition also. Attention can be useful. And they have said an image recognition module with attention does much better than an image recognition module without attention. So anyway, I expressed to you in a very broad terms, but how exactly they use, how do they figure out the alpha values and so on, might be quite different. Okay. All right. Any other question? Okay, Deepu, you have a question. Okay. Go ahead. Okay, Deepu, I've tried to unmute, but didn't seem to work. Okay, that didn't work. Anybody else have a question, or is it a system-wide problem here?
I have a question.
Ramkiran, you are alive, well and well. Okay, go ahead.
Sir, from looking at data and type of data, how do you decide where attention is required, where it is not?
Okay, you're asking something about the data. I didn't hear you clearly. You had a question about the data for machine translation. Okay, go ahead.
No, sir. This attention model, like how do we choose when it is required, when it is not required?
Oh, okay. That's the beauty of all these neural networks. We don't go ahead and program anything. We are allowing the system to learn on its own. It is looking at massive amounts of text. You look at the amount of data. BERT, for example, we haven't come to BERT yet, the attention model. They give some numbers, billions of words of text and things like that. They've trained it on all of that. And it is aware of all kinds of combinations of things, how words occur, co-occur. They're looking at correlations, figuring it all out. And so it is automatically figuring out when is this association happening. And so it figures it out for you. We don't go about saying eating goes with apple. We don't say eating does not go with chair, so on, right? So it's figuring out these correlations that occur naturally in natural language text. Of course, there might be strange cases where somebody's eating a chair, but the occurrence of that would be rare. It's all statistical, figuring out all of this in an automatic way. So the deep learning network figures that out for you. All right.
No, sir. My question was like in natural NLP, attention requirement has come, right? Like these words are more related than the others.
Right.
Someone was asking about the images. So how do we tell in the first place that for images, attention is actually required?
This is, again, it has learned the correlation between, let's just take that example of the ear of the dog and the face of the dog. There is some kind of a correlation between the two. And if there is something uncertain about the face of the dog, or we need to predict, we're saying the ear is already telling you that there is a higher probability that that is the face of a dog and it is not the face of, I don't know, human being. We don't have the kind of ears that stick out on top of our heads. In a dog, the ears stick out on top of their heads. It doesn't happen with human beings. So is that a man or a dog? We're saying with that pointy ears, it is able to say that's a dog, most probably a dog. It is not a human being. So this is the kind of intuition that might be going on. Again, neural networks, as you know, they are notoriously numbers oriented. They are not intended to be able to explain to you, how did you say it's a face of a human, of a dog, not a human being? It is saying, well, I found the tension between those ears, the pointy ears, that got a little bit more weight. So it favored a dog and not a human being. That's the kind of explanation attention may be able to give you. So that's what it's figuring out, that correlation. All right. Okay. Okay, so good. I'm glad you all had some questions. Please take a look at my next lecture, which is only on attention models, and come prepared with some questions and dialogue, so we can do
Sir,
that. Okay.
yeah.
All
Sir,
right. Maybe one last
so,
question we can take. Shreya, you have another question?
yeah, no, sir, this is a, sir, I want to ask you, what is the final submission deadline for our
For our
assignment?
class project, that is a separate dialogue I need to have with the TAs. I think we originally decided for the first of the two remaining projects, April 15th was the deadline, and the second one was May 15th. But I'll confirm it. In my mind, I don't know the exact date. So if you have any thoughts about it, please go ahead and inform the TAs about it. And we'll make the conclusion. That's another week away. Today is the 8th of April. We have another week to go.
Yeah.
So let's aim for something so that we don't have both of them due at the same time. And if you're having real problems with your internet connection, with whatever, please let us know. Our goal is to accommodate you as much as possible. We realize that some of you may be away in small places and environments that are difficult, but we'll try and accommodate you. Okay. All right.
Okay, sir.
Okay, so have a nice week, everyone. Stay safe, and we'll get together again on next Monday. Okay. All right.
Thank you, sir.